So good morning, everyone, and welcome back to today's session. For those who are joining just now, the link to the recordings of the previous session will be available in Discord as well as Hype. Please do check it out while there are any doubts while working in the project. So now, without any further delay, let's dive right into session. So just before we get started, I'd like to remind you that you will have the chance to raise questions to the speakers by posting it into the chat box. So you may send in your questions at any time during the presentation or during the Q&A session. We'll be addressing them. And please feel free to make this session an interactive one. So without any further delay, I'd like to introduce the presenter of the day, Mr. Rajesh K.Jeyapaul, sir. So Rajesh K.Jeyapaul, sir, is an engineering lead for AI Ops at IBM Labs, India. He is an IBM Quantum Ambassador, initiating the quantum computing enablement for clients. In his 25 years of technical journey, he has led multiple transformational projects on various technology stacks, ranging from operating system to cloud, and on emerging technologies like cloud, IoT, and AI. His current exploration is around quantum machine learning. He has co-authored various technology books and has 6 patents to his credit. He started his career with the Indian Defense Research Organization as a research fellow. He did his engineering on electronics and communication at Karunya Institute of Technology, Coimbatore, and further went on to complete masters at BITS Pilani. Also, he did his master's in business administration at Madurai Kamarajar University. Sir, we request you to take over, sir.
Thank you so much, Madam, for that wonderful introduction. Hope I'm audible.
Yes, sir. Yeah.
Okay. Yeah, CIT and Coimbatore is not very new to me. After my 12th, I think 1990, I did my, the entrance coaching at CIT. And it was a very good experience spending time at CIT for that coaching, I think a couple of months. And I would say that those days we used to have this .1, .2 concept. So I think 0.4 or 0.6 marks I missed to get the .1 college. So I went ahead and joined Karunya, Coimbatore. And now it is 25 years has passed by, and really happy to give this talk for the CIT students and the faculty members. And I'd like to thank the Manjula Madam for giving me this opportunity. And my wife also did her ME at CIT. So we are close to CIT. Yeah, thank you so much again for the opportunity. And so today, let's understand, I think this is a series of discussion I think you are having around quantum. So today, let's try to understand a little more about the quantum machine learning. And few things we need to touch upon. Some of the basics we need to be very clear. Okay, I'm sure most of you would be having the experience on working with machine learning, right? And so let's be a little bit more interactive so that we can get the core concepts clear, okay, from quantum perspective. All right. So this will be the agenda, and just want to understand how far you are exposed to some of the basic concepts. Okay. So if you could respond either in chat, or if audio is enabled, audio is also okay. And this is where I need to switch to this window. Okay, so I don't see an option where I can have only the chat in front of me. But anyhow, you can use the chat window also. Can you go ahead and respond any two basic principles of based on which quantum computing is working? I'll give you 5 seconds. I think you can chat, right? Let me say hi to the chat so that you see my chat.
Like that is enabled, you can give answers in the chat box. Is enabled.
Okay, superposition, Nandana, thank you so much. Right, so superposition is definitely one of the thing, and another main thing is entanglement. So superposition, like in the classical computer, we deal with bits 0 and 1, isn't it? But when it comes to quantum computing, we are making use of the basic, the operating principle of the electron, isn't it? Which goes into different states, right? So it oscillates up and down, left and right, spins, isn't it? So that we kind of make use of that principle for our compute requirement, right? So that's why we say that for the quantum computing we will have 1 0, and also we will have a state which will be in both 1 and 0 state, right? So that is superposition. Entanglement, that again nature has given this to us, where the one, if one electron is in one state, the other electron could be in another state, right? If it is one electron is in state ground state, another one will be in the high energy state. If it is one electron is in state 1, another will be in state 0, like that. Okay, this is an entanglement principle. And Einstein mentions this, right? God does not know how to play dice, right? Basically the message he is giving is, nobody knows how this behaves. And I think the teletransportation, the experiment which China does, they had one electron in the ground lab and another at the space, and they observe the same behavior, right? So that is something, we are making use of it for our computing requirement. Okay. The second question: classical computer does not complement quantum computer. Let me switch. Yes, Utkarsh Sharma, superposition and entanglement. Yeah, how about this one? True or false? Classical computer does not complement quantum computer. Okay. Nandana says false. Any other response? Okay. So it is false in the sense, yes, both, classical and computer has to go hand in hand. Okay. They complement each other. Okay. This is another very basic message we all should be aware of. So we will not come out of the classical computer completely and then depend on the quantum. Okay, so that's something we need to be aware of. But there are various reasons into it. One quick example could be if I say 4 into 3, what it is, then we all will say 12. And when I say that, okay, get me the factor of 12, okay, then we will take a little bit more time, isn't it? So now you keep this example in mind. So the classical computer has the capability to quickly do the multiplication, right? 4 into 3. But the quantum will take more time to do this. But when we say that, okay, take the factor of 12, right? Classical will take a little more time. Okay. But the quantum has the capability to get you the response, the factors of 12, right? So that's the reason we need both classical and quantum. Okay. So is quantum computer always faster than classical computer? So I think this we discussed just now, isn't it? So right, so in some case classical is fast, in some case quantum is fast. And what we need to keep in mind is, in the exponential space, whenever the computation goes into the exponential space, we need quantum. Okay, right, hope this is clear, the basics. Okay, the another thing we need to keep in our mind is, can you help me to structure this machine learning pipeline? It is a little scattered here and there. Where we will start? Again, use the chat window. This will help me to align, right, what we do with classical with quantum. Right or wrong, you can give your understanding. Okay, I think anyone wants one more. Okay, what will be the first step? At least you tell the first step. So when it comes to the machine learning pipeline, right, we all aware that we deal with data, right? So we try to extract some, pattern from the data, isn't it? That's what we do. So now let me ask this question. How many of you are new to load and Deepak, load and split? Exactly. Yeah, feature extraction comes after load and split, but a good start. Okay. So how many of you are new to YAML? Let me understand this. I think roughly we have 18, 19 people, right? So let's see how many of you are very new to machine learning. Okay. So one person. Okay. So let me understand that. Okay. Yalamudam, Niranjan. Okay. Right. So if it is 50-50, I will change my discussion in that way. Now it looks like 20-80. Okay. Isabella also. All right. So 30-70. Okay, good. So most of us looks like aware of it, right? Machine learning. Okay, good. So when it comes to machine learning, I think I will quickly get into this one so that people who are new also will quickly understand this. 1 second. Okay. All right. So now I'll take 5 minutes to explain the basics of machine learning. Okay, then we will go back. Okay, so that let everyone be on the same page. So there is an equation given y is equal to f of x, and there's a data set available. Okay, weight and height, and there's a simple, the linear equation is given. Weight is equal to b0 plus b1 into height. B0 and b1 are all coefficients. Okay. Now with this data, I'm asking you to find the coefficients b0 and b1. Okay, I will give you 10 seconds, right? Take this data, fit into this algorithm, and then get me the value of b0 and b1. Okay, so your time starts now. Let me give 10 seconds. Hope this equation is visible. Okay. Still no response. I'm expecting the 70% of you who knows machine learning to at least, or this anyone can respond. This is nothing related to machine learning. I'm just moving up and down to see is there any response in the chat. Okay. Usually when the presenter share his or her screen, that chat, I can have a small pop-up at the right hand side, but with the Google Meetup, I couldn't get that. All right. So now take the assumption that, okay, let B0, you can neglect B0. Weight is equal to B1 in the height. Now you tell, what would be the value of B1? See, later on, we cannot come and complain that, machine learning computer has taken our job. Okay, now who is fast, whether machine or us? Okay, so let's take the simple example. What would be the value of B1? Okay, see here I've given the data, the right hand side. So of course B1 is equal to weight by height, agreed. But now use the data, find the value for B1. Take any one data. See, this is what machine learning does, isn't it? What we give the data, it takes it, fits it in the equation, and then it tries to find the coefficient. Okay, so this understanding is very important. Then only you will appreciate why quantum. Okay, why we make machine learning quantum. Okay, well, at least I need one response, right or wrong. You just go ahead and tell why, because that is how the machine learns. Okay, now the problem, the problem whatever given, right? Yeah, good, 48. Yes. So that's what I'm saying, right? Right or wrong? Just go ahead with your response. 48. 0.48. Okay. So I'm not saying wrong here. Okay. So whatever, right? So you say is correct. Okay. It's 47 or 0.47. I'm sorry. I'm using my specs now. Okay. Thank you. All right. 0.47. Good start. All right. Okay. All right. Yes. Thanks for your response. Good start. The point here is we have to start somewhere. Okay. Now let's take weight as say 90 and then height as 180. all right? And you will get whatever 0.5 or whatever it is, isn't it? Or 0.47. That's how something closest you are saying, right? Now, can you validate your value of B1 with this data? What happens to your response for 0.47? Goes for a toss, isn't it? Right? This is how machine learning works. Okay, whenever we give the data, right, it will try to kind of take the data, fit into the equation, trying to find the coefficient. This is what exactly happens. This is what is machine learning. Okay, but when we try to come out with a new set of data, right, then the computation whatever we have done, right, is something may not fit with whatever we have observed earlier. So what we have to do, either we have to throw this data out, okay, right, or like you consider this as an outlier, and then either you change the 3800 into some average value of the given data, average of 165, 178, 180. Okay, this process is called data cleaning. Okay, so whenever the data is given, they will find, okay, is there any outlier, right, which is going to disturb my equation. So what I will do, I will remove it, or I will take average. Okay, that is what they will do. Okay, and then they will kind of validate with one more set of data, and then they will see the closeness. Okay, so this is the overall approach of how the machine learning works. Given the data, right, we kind of split the data into training and the testing. Okay, so that using testing, training, we will compute the coefficient, and then using testing we will validate it, right? And then probably we will do the pre-processing, and then the feature extraction. Okay, feature extraction is nothing but here I have taken only one feature, which is height. Okay, I think height is the x here, and weight is the y here. Okay, so now if there are more features, okay, for example, body mass index, age, everything comes into the picture, then those are all become x1, x2, x3, right? So now that feature, like extraction is nothing but, okay, what features are relevant? Okay, there is another processing that happens. So that is primarily the feature extraction. Okay, and then we fit it with the algorithm. That is nothing but find the coefficients, and then kind of validate. This is the basic pipeline. All right, hope you got it. Now, how we narrow down this value to B1, that is a very next important thing. Okay, since we have discussed this, I will quickly take you through that as well, then we will go back. Okay, now keep this equation in mind. B0 is weight is equal to B0 plus B1 into height. Okay, now madam said that it is 0.47. Okay, right, we start somewhere. That is called as a global maxima. Okay, and our ultimate aim is to reach global minima, which could be the closest value of B1. Okay, in this example what you have taken. All right, but while computing, okay, we may get into some value which may not be the actual the global minima. Okay, that we call it as a local minima, right? So what we do, we start with say 0.5, that is global maxima, then we will come to 0.7, right, and then come to 0.47, then come to 0.474, something like that. Then we feel that, okay, it is good, and we'll stop our computation. Okay, right, which is not the expected one, because our goal is to reach here, right? So what the approach is, take some random value. Okay, slowly you kind of learn, right, and then try to avoid this kind of local minima and then reach the global minima. Okay, this is in plain English term. But when it comes to the mathematical way, it is more of the finding the the maximum minimum, what we have studied in our the class 12. Okay, first order differentiation and the second order differentiation. So you differentiate, right, and the second order differentiation will tell you if it is negative or positive, right? If it is negative, you are slowly coming down, right? If it is positive, you are slowly climbing up. Okay, so what we need to do is we have to slowly come down from that value of 0.47 to whatever the closest value, isn't it? So that is what it happens. So mathematically, that was it, internally it happens. So this we call it as an optimization. Okay, so this optimization takes time, right? So for the machine to try it out with the different values and come back to us saying that B1, this is the value of B1, right? So when it comes to machine learning, one is this pipeline. Okay, take the data, split the data, clean the data, fit it with algorithm, validate it. And second core thing is this optimization. Okay, the coefficient, finding the coefficients. Okay, so that is why they are giving lots of tuning parameter for us, like learning rate, right? You might have seen that learning rate. If the learning rate is very small, you will take very, very small steps, and there is high probability you will get into this local minima. If the learning rate is a little large, you will kind of take a bigger jump and you can avoid local minima, but the accuracy also will go down. So there is a balance between this learning rate, whether it is small or big. That is why we do multiple iteration, and that is one of the reasons for machine learning we need more compute environment. Compute capacity has to be there. Okay, so this is the basics of machine learning. Let me quickly understand. Is there any questions? Is it clear? Those who have said no to machine learning, at least you got the basic idea of what is machine learning? Yep. Okay. Thank you, Nandana. All right. So this is what it is, right? Now let me quickly go back to our discussion. All right. So this is the actual pipeline. Split the data, process the data, do the feature extraction, okay, and then fit the data with algorithm. At this stage, you keep this in mind. It is B0 plus B1 into weight. Okay, that is a very simple thing. But when it comes to a complex data set, complex algorithms are used, right? And then we try to reduce the loss. That is the optimization, what we discussed, right? The global minima and local minima, stuff like that. Okay, then we finally get into the classification. Okay, we need to be aware of this. Well, because when we get into the quantum, right, what part of this can go into quantum, what part can handled by classical. Okay, now that's a linear equation what I showed you, b0 plus b1, right? Now when it comes to a complex data, right, and identifying an object, right, or identifying whether someone can invest in a stock or not, right? So that involves too many parameters, right? Various features has to be considered, right? Historical data, the rate at which the stock is going, right? And yesterday's value, last year's value, and things like that. So the computation becomes a little complex. Okay, now one such algorithm which is widely used is SVM, right? I'm sure those who are all familiar with machine learning might be aware of SVM. Okay, now what it does is this SVM algorithm, okay, helps us to classify, okay, or segregate, okay, whether yes or no, circle or square, something like that. Okay, whether it can be invested in this particular stock or not, isn't it? That is called as a classification. Okay, now this algorithm, right, uh, tries to create a line which separates this yes or no. Okay, right, separates this circular box, separates whether someone has a disease or not, right, like that. Okay, so this algorithm mainly does that. Now the objective of this algorithm is to have a line, okay, which clearly separates so that they don't overlap. Okay, finding this is an optimization problem. Okay, we all should be aware of this is very complex one. Okay, now if you see that when the data is given to us, okay, here, right, assume a simple data, green and red dots, right? If we ask us to have a separate line dividing this green and red, it is difficult, isn't it? So when in the real world problem, it is not possible to directly have a line which separates this green and red or yes or no kind of a thing. Okay, so what this algorithm does is take the data, right, and then do the cleanup. Okay, and then with the remaining features x1, x2, x3, x4, it tries to kind of find a hyperplane which divides, right, the label y. Okay, whether the loan can be given or not, right, whether the stock can be invested or not, or whether this is a cat or a dog, right? Something like that. Okay. So how it does is it visualizes this data in a higher dimension. Now it is in a two-dimensional one, X and Y. Okay. What the SCVM will do is it will visualize that in the higher dimension. So now you see X, Y, and Z, and clearly we can have a separate division between green and red. Is that clear? This is what it does. Okay. But how it does is like this. Though we say that, okay, we are moving this in the higher dimension, but actually what it does is it finds the distance between the red and the blue, or the distance between the features x1 and the x2. Okay, that is what happens. See, everything is mathematical operation, isn't it, right? So now through that only we are kind of moving the features from the lower dimension to the higher dimension, and we all know that why we are moving that to the higher dimension. Why? Because we have to have a separate division between the yes or no kind of a thing. All right. So it is again our class 12 max. It's a dot product. Okay. A dot B is equal to AB cos theta, right? Or cos theta is equal to A dot B by mod AB. This is what we have studied. And what happens primarily here is a dot product. Okay. Now the dot product is a mathematical operation which happens, and our intention is to kind of, have that hyperplane created so that the separation happens between the, the yes or no thing, right? And now the coefficient here, right, is basically the distance, okay, the R, right? That is what is the coefficient here. When you want to map this with a simple equation, our coefficient is B1. In that, weight is equal, height is equal to, B1 into weight. Okay. So here that R. So ultimately we boil down to finding some coefficient values. Okay. Now, when we want to visualize that in a mathematical manner, right? What is the dot product happens? This is what internally happens. Okay. So this is the Taylor series, right? We have the factorial, we have the exponential, right? We have the, the dot products, right? This is what internally happens for, us to get that coefficient value. Okay. So I'm making it a little simple for us to visualize that our requirement is here, right? For the, to understand what is the computational requirement of the algorithm. Okay, keep that in mind, right? We are not trying to deviate from why quantum, right? We will align to this, but we need to appreciate this. Why? Because this is what SVM does internally. It is all a mathematical, operation, just for us to say that whether that is cat or not, right? Whether that person is wearing mask or not, right? Whether that person is, or whatever it is, what is the object, right, on top of the table or not. Internally, you see only this mathematical operation happens, right? Whatever the data we give. Okay. So our point of view here is these are all high computational thing which happens within the algorithm. Okay. So this is what SVM does, right? And let's understand now, quantum, what is the role of quantum here? Okay. But let's see, maximizing the support vector distance from the hyperplane. So the support vector machine is nothing but, the circle and the box which is closer to that line, green line, are called support vectors. That is why this algorithm itself is called as support vector machine. Okay. So now the question here is, maximizing the support vector distance from the hyperplane is what task it is? Is it a linear task or non-linear task, or is it dimensional reduction? At least I need 2 responses so that. So whether it's a linear, how many of you say it's a linear optimization task? How many of you say non-linear optimization task? This is certainly an optimization task. Okay, we all should be aware of it, right? That other chart I showed, right? Global maxima and minima, right? We are coming from 0.47 to the closest value, right? That is the optimization task. Okay, right? So this is, yes. So Shana Jayachandran has mentioned this is non-linear, right? Yes. Yamuna madam mentioned this non-linear. Okay. This is non-linear optimization task. Okay, keep that in mind. Why? Because these are the few things we will map it with our quantum. So the kernel trick is nothing but moving the data to the higher dimension, right? So that is what we saw, isn't it? So moving the data to the higher dimension is nothing but taking the dot product, right? So that is why it is true. So that is what is called as a kernel trick. The kernel should not be misled with operating system kernel. Okay, so don't get into that kernel. This is called as a kernel trick. Why? Because it is internally we are doing some magic, nothing but the dot product, so that we will visualize the data in the higher dimension, so that we can clearly separate the red dots and the green dots. Okay, so that is the intention there. Okay, so with that background, let's step into this, why we make machine learning quantum. When it comes to the quantum world, okay, and we all know that, okay, we are trying to get the high compute environment from the quantum, right? So now you visualize in this way whether the data is quantum. So what we mean by that, right? Whether the problem is quantum, what we mean by that. Okay, so that idea we should generate. Okay, so what kind of problem we can consider as a quantum? Any example? Anyone has any example? What kind of what kind of a problem can we solve through quantum? Any real world? Don't get into the mathematical part. Image processing. Okay, we'll come to that. Some real world problem. See, I'll give a couple of examples. Stock market prediction. Yes, madam. Right. Stock market prediction. Why? Because it deals with complex, data points. Okay. So lots of features are involved, right? And then optimization. Stock market prediction is one thing. Minimum support price for the farmers. That's a very complex thing, right? So that's why our farmers are also, trying to get the help from the government, right? Because it is very challenging to fix a particular price. Traffic optimization, yes, Kaushik, yep. Huge processing, Deepak Kumar, yep. All right. Couple of thank you. So a couple of more example is finding the right fertilizers. Okay, and the chemical, the interactions, right? The molecular interactions, right? The behavior of that, right? If you understand that better, we will be in a position to find a better alternate fertilizers. And then finding a battery which can last long, which is more economical, right? So there also the research is happening where people are trying to uh, understand the the lithium and oxide, right? That's the current battery combination, right? And now they have taken lithium and the sulfide. Okay, Daimler is working with IBM on that, and they are trying to understand and study the behavioral pattern of these molecules, right? So that whether we can kind of go ahead with this combination for the battery, right? And yes, drug is another thing. It's a very valid the real-time example, we can say. All right. So there are 2-3 examples we discussed. Okay, one is of quantum in nature, right? This battery, fertilizers, drug. Why? Because this deals with the molecular component, which itself has a quantum behavior, isn't it? So when lithium and oxide interacts, what happens to the electrons, right? Which is how that bonding happens and things like that, which basically based on this quantum principles, right? So this is one quantum data, right? And we are solving the quantum problem. And if you take website, traffic optimization, stock market, right, we call this as a classical data. Okay, but it's a quantum problem. Okay, so that is how we need to visualize, right? When we slowly get into this, given a problem statement, what it is, right? So you'll get the clarity. Okay, image processing. Okay, definitely, I think fast Fourier transform will be applied over there, I guess, FFT, isn't it? So optimization, okay, and right. So that is a classical data with the quantum problem nature. Okay, so when we come back to this slide, that is what we are discussing here. Okay, so there are some quantum problem, quantum data. Okay, QQ. There are some classical data, quantum problem. Okay, and there are some quantum, data, and there are something is suppressed in the classical. Okay, so here, when it comes to quantum machine learning, the focus is primarily around this red square. Okay, classical data, quantum problem. Okay, so why we are saying quantum? See, rest of the things you will easily now understand. Okay, why we are saying that we need quantum, right? We have seen couple of examples, right? The simple weight is equal to height equation, and then the SVM, what happens, right? This kind of computations, that exponential dot product, isn't it? All those things are all little in the happening in the polynomial space, isn't it? So when it gets into that, the high level of computation, right? We know that okay, quantum is better. Okay, so that is why, right? We are saying that quantum can be applied over there. Okay, and then another complexity is this highly correlated distribution. So the features X1, X2, X3, right? When you want to say that whether to invest in a stock or not, so we will take various features. So the stock price and the company name, history of that, right? All those stuff. These are all highly correlated features: X1, X2, X3. What to leave, what to consider, and then kind of finding a coefficient among these features is again a complex. Computational requirements. Okay, so that is another reason we can boldly say that we can get into the quantum. Okay, so that is in a simple term, you keep this in mind that okay, any high compute requirement we can look for quantum. All right, so this is how we visualize, right? We have the data. Okay, X the features, Y is our target. Okay, which is given to the quantum, and come back. But what is the challenge is, okay, the data is not quantum here. Okay, this is classical data, right? Keep that in mind. Why? Because why I'm specifying that is the approach towards quantum ML, you will appreciate later on. Okay, the data set what we will have it in the Excel sheet. Okay, name of the stock, right? Whatever it is, the price of today, yesterday, closing day price, opening price, right? All those X1, X2, X3 are all represented in the classical data. Now, when it comes to quantum, okay, the requirement is this classical data should be represented in the quantum. Okay, this is the first requirement. Okay, that is why, we discussed about this classical data and then quantum problem and all those stuff. Okay, but when it comes to the quantum machine learning, right, we need to be very clear that the data what we are, representing, okay, are represented in a classical manner, right? That X and Y has to be mapped to quantum. Okay, what it is, we will understand. But this graph will give you the insight that okay, the work has already started towards this quantum machine learning algorithm approaches and all this stuff, right? But now it is started maturing. Okay, right? So recommendation is there. Okay, clustering, SVM, right? And now only we are maturing in a way that okay, how we can kind of clearly take the advantages of quantum. So that is called as a variational. Okay, that is a variational quantum. Okay, that's a Boltzmann thing. But now that variational quantum machine learning is the current thing, primarily used by the research, academic, and also the industry community. Okay, so the first step what I told you is take the data, okay, map it to quantum. All right, how that mapping will happen, right? So which is called as data encoding, or it is called as feature mapping. Just terminologies, be aware of it. Okay, feature mapping is nothing but you are mapping the classical data to the quantum. Okay, so the data encoding, there are a couple of approaches are there, right? And just a one-to-one mapping you will do basis encoding. Okay, or what you will do is take a feature x and then you will kind of encode with the amplitude, right? Why? Because qubits, you all know that it has the amplitude and the phase, isn't it, right? So we can do the encoding using the amplitude, that is called as an amplitude encoding. Okay, and then called angle encoding. You take x, right, and then kind of encode it to the qubit with a particular phase change. Okay, a rotation you will give, all right, and then that will be mapped from classical to the quantum. These are some of the basic thing, but the important point we need to be aware of is, okay, minimal usage of qubit is always recommended. Okay, which way is better and is all those stuff, it is our call. Now if you say that there are 4 qubits, right? Now we can map 2 classical data here, even you use the amplitude encoding, right? And but here when you have 4 qubit, we can map 4 classical data. Okay, so angle encoding would be a little better compared to amplitude encoding, right? So that is the only criteria. But these are the different ways we can map our classical to the quantum. Okay, but we all should be aware that, okay, try to have minimal number of qubits to represent the classical data. Okay, and this is another encoding, higher order encoding. Basically you take the feature, okay, and do a rotation, right, and then do a dot product. This you can easily understand why, because we are just trying to bring in various combination to just map our classical data with the quantum data. So now for people who are very new to machine learning, you understand this x1 x2 as your feature. Let's take the initial example, weight is equal to height. Okay, I think that the weight is y and height is the feature x1. So in this case, our requirement is to map this x1. We don't have x2 here. Okay, map the x1 to the quantum qubit. So what we will do, we'll take the x1 and then we apply an Hadamard gate. So you all know that Hadamard gate will put the qubit in a superposition, right? So we will take that x1 that will be in a superposition state, and then we will do a phase rotation. Okay, z angle phase rotation. That is what rz the x1 happens, right? Since we don't have one more qubit, I think we are not considering that, right? But that is one way of encoding. That's it. Take feature, apply the Hadamard gate, and then do a rotation. That will become kind of an encoding for us. Okay, so visualize it in that way. Why all these steps are required? But that is a requirement. Take the data and then kind of do the mapping to the qubit. Okay. So the question is, does quantum computing reduces the amount of data required for training? What's your response? From the machine learning perspective, we know that, for training, we need considerable amount of data. Yeah. So there's no kind of mapping with respect to the data, right? But from the machine learning perspective, what is the the level of data we are looking for, right? Basically the over learning, right? All those things you are aware of, right? So that is still applicable over here. Okay, so can quantum reduces the training time? The answer is yeah, definitely yes. Okay, it speed up the training time of the classical model. Encoding the classical data to the quantum state is called, this is what we discussed, right? Feature map. Okay, or it is simply called as data encoding. So we all know that the first step is take the data, right, feature, and then you map it with qubits. This is the first step we need to do when we do the quantum machine learning. Okay, so this one is called the amplitude encoding. Okay, we discussed on this. Yeah, just be aware of this also. Okay. Any question here before we get into variational quantum? The topic might be a little hard if some of the basics are very new, but otherwise it is very, the basic approach only what we are discussing. So you learned about machine learning, okay, and you understood the optimization that is involved in the machine learning. And now when we step into the quantum, you know that, okay, the first step is we need to encode our data, classical data, into the machine learning. Okay, that is what we have seen so far. Okay. Now with the variational quantum algorithm, now I think we will take a simple example. Yeah. So let's take our B0 plus B1 into weight, right? The coefficient B1, okay, to find that, right? So the variational quantum algorithm. So rest of the things now you can easily map. Take the data, do the encoding, right? And then compute that coefficient B1, okay, with quantum. That is called as variational quantum algorithm. That's it, right? For in a simple way to understand this. Okay. So any algorithm, if you take, there will be some coefficients to find here, right? I have given an SVM example over here. All right. So the same, all the computation, whatever we discussed to find the coefficient value, right? That can happen in the quantum. Okay. So now the approach wise, right? Now the next step is, okay, let me understand this. How many of you are aware of a quantum circuit? What is quantum circuit? What is your understanding of quantum circuit? Why we need quantum circuit? Reversible. But let's start from little basic. Why we need quantum circuit? Fast. Okay. Any other response? Okay. Now, the coming into the quantum world, right, might be a little challenging initially. Okay, but let's make it very simple, right? The classical and quantum are two different world altogether. Okay. Now, quantum, we know the basic principle, superposition and entanglement. We discussed that initially. Why? Because if you take an electron, all right, that electron will spin, right? It will oscillate. Okay, we are making use of that principle for our high computational requirement. Okay, that we discussed. Now, assume that, okay, there is a quantum computer. We have kept two electrons inside that. Okay, what next? How we will give this the data, whatever we are talking about, this feature x1 x2 height weight to this electrons? Isn't it that question we have? Isn't it? So we need some operation, right? We need to do some operation on that electron, right? So that one thing is we will represent our data. Second thing is we will do the computation. So for that only we use the quantum circuit. So for you to easily understand, you consider this as a kernel program in the operating system. Kernel is the one which interacts with the system, isn't it? If you want to write into a port, read from the port, right? All those things we use the kernel calls, system calls, right? Like that, this circuit. Now what you see here in my screen, this is the circuit representation. Okay. So in the quantum machine learning world, the opportunities are we need people who can write Python program, okay, and do this quantum computation. Okay. who may not really need to know about this, the quantum mechanics, the physics behind that, not required. Okay, so I will show some of the Python program which everyone can do it, right? If they have this basic understanding. The second requirement is we need people who are who can generate these circuits. Okay, the circuit is the one which will implement your algorithm. Okay, what it will do is it will try to play with that electron which is there. We call it as a qubit, right? So that is why we call this as a gate. Okay, right? So the Hadamard gate H will put your electron into the superposition state, right? It will oscillate up and down. This RZX1 will put your electron to spin, right, in the Z direction. Okay, so keep that in mind. So that is the circuit we are talking about here. So why I took that is when it comes to the algorithm, at the high level, get this understanding that you take the feature, we map it with the quantum, thing. So we call that as an encoding or feature map. And then we give that data, which is now mapped to the quantum, to the, an algorithm, which will, go through some circuits like this. Okay. And then help us to get the coefficient. P1 in our basic simple example. Okay, keep that in mind, right? Let's not complicate. Later on, we can kind of get a little deeper into this. All right. So when it comes to like the design part of this quantum algorithm, right? And usually the qubits is represented in a block sphere like this, right? So in a very simple way, you can show that okay, the qubit is in state 0 or 1, or you can show that okay, it is in the superposition and also spinning in the Z direction, right? Or the quantum is made to oscillate in the complete block sphere. Okay. Now this is one of the design principle. Okay. So the what is expected from the academic is, right, go a little deeper into this part. Okay, how I can design an algorithm. Just give me a second. Okay. All right. So how we can design an algorithm? Okay. Right. So for the academic, should think a little bit more around that, right? And no, I've given a reference to the paper from where I have taken this. So this is their approach, right? They take the qubit after being encoded, right? And then what they try to do is they will try to uh, create some logic where it goes through some rotation, and then kind of the C0 logic, whatever I have mentioned over there. Okay, I will not get into this, right? But this will help us to get the coefficient value B1 in our case, the simple example, right? Or in the SVM, that the distance R. Okay, so that is what we need to know, right, at this stage. But this circuit, right, can be improved upon. Okay, that is where the academic should pitch in and see that okay, in what way this computation can be implemented, right? Work with the qubits that are available, okay, and then kind of get the result back. Okay, so that should be our focus. So keep that in mind. But that is what it happens. Okay, so variational quantum algorithm, what it does is it takes the classical data, okay, converts into a qubit thing, and then find the coefficient. And what next in the machine learning pipeline? It is obviously reducing the cost. Okay, in our example, you mentioned 0.48, 0.47, right? Now that we are trying to reduce it and come closer, okay, to the global minima. Okay, that is the error reduction part. Okay, so that computation will happen. Okay, so that is optimization here we discussed about earlier. Okay, that complete optimization also is done through quantum. Okay, and then we get the result back. So there are various algorithms available. Okay, at this stage I'm not getting into the the circuit level, but make a note of it. Okay, so this coefficient computations where the exponential computations are happening, and then the optimization, right, where so many iterations are happening. Okay, so for these two we kind of go and approach quantum. Okay, so quantum approximation optimization algorithm is one thing, right? They have come out with a circuit like this, which will help us to get that coefficient value, and then the optimization what we are doing. Okay, right? And this is another approach, right, where the green ones completely happens at the classical level, and at the blue ones completely happens at the quantum level. So when it comes to quantum machine learning, we are aware of the quantum machine learning pipeline now, right? And we know that what is our first step, that is encoding the data. And then we know that, okay, we give it to quantum to do the computation, right? And come back to classical world. Okay, so this is the overall picture you should be aware of. And then the academic focus, the research focus should be primarily around the circuits, right? Building the circuits. Okay, so how effectively, I will work with the electrons which is given to me, so that I will get the computation done and come back. Okay, so that is the focus, right? Basically, we need to focus from the academic perspective. Okay, and now the last step is our target Y. Okay, Y is equal to f of x. Our target Y is nothing but whether to invest in a loan or not, right? Things like that, isn't it? Whether there's a cat or not, right? That Y, how we are going to extract. Okay, so there is a little, if it is a classical, we know that, right? If it is 0, it is false, or 1, it is true, like that we can go, right? But when it comes to quantum, okay, it will come in a qubit manner, right? So how we will say that it is yes or no? Okay, some logic is applied. These are all very academic thing, right? And there are many approaches probably we can come out, right? And that's another scope for the academic to kind of come out with various ideas on this, right? But here, okay, the one approach is pair post processing. Okay, this again is taken from one of the paper, right? You can search for it, right? Ultimately, when the computation is done, and once the optimization is done, we need to know that whether what is the height of the person, or what is the whether to invest in a stock or not, or whether someone is wearing a mask or not, right? The classification thing. How we will do that at the end? Okay, the qubit will come out with the state, and then we will try to measure the state of the qubit. Okay, so now it is basically the even parity, odd parity approach they have taken, right? If it is even, they consider as something like yes. If it is odd, something like no. Okay, so that is a computation they have done over here. So finally the state of the qubit we take, and we just take the parity of that, and if it is even, we say that yes, you can go ahead and invest in the stock, like that. Okay, so our understanding should be, when it comes to the machine learning quantum world, first step you encode the data, second step you give it to quantum for your all computations, third step you convert. Why? Because this is something like decoding, right? You convert that output, the qubit, into a normal classical representation of yes or no. Okay, so this is something we need to be aware of. All right, and yes, this is the basics of the quantum machine learning. Okay, I will not get into the other part, but let me understand whether you got the the basics of how we are approaching the machine learning for using quantum. So next I will show a quick demo, and you can try it out. We can spend 10-15 minutes. And but before that, I would like to ensure that you got the basic flow of why we need quantum for machine learning. Any question? Is there any other question I have? Okay, what does this blue and green indicates here? Okay, what does this blue indicate? Let me know. This flowchart shows you what we do. Okay, when we give the data, how we are approaching the machine learning. Okay, now what is green here? What is blue here? What is blue here? Okay, Yal Amudan is saying blue maps for machine learning. Deepak is saying green feature extraction. Okay. Okay. So, Madam is correct. Blue is done using quantum. So that's the idea here. Jayrani also is saying blue is quantum. Green is classical machine. Yes. Okay. So that's the basic idea here we need to get. Okay. So feature map, we discussed encoding, right? Machine learning, everything, happens at the right. Okay, data encoding, everything happens at the quantum level, isn't it? So that is the idea, right? Overall basic, the takeaway I would say. PCA is a normal, the principal component analysis. Okay. And all that computation, no, I think eigenvector, eigenvalue, all those things are all, happen at the classical level. Do all the stuff, throw away all the unwanted features. That is what the PCA does, right? So if you want to predict something, or if you want to identify cat or not, all unwanted features like the surround, any outlier, everything you remove it, okay, through PCA, okay, and then you step into the quantum world, do the encoding, and then do the rest of the stuff. Okay, very good. All right. So now let me quickly show the sample program. I have put this in one of the GitHub. Okay, it's asking for authentication. Yeah, I think there are two programs I've uploaded, and this I will put it in the chat window as well. Okay, and so what you can do, if you are in front of the system, go to quantum-computing.ibm.com. Okay, let's give it a try, another 10-15 minutes maximum. So can you all log into this quantum-computing.ibm.com? I will put it in the chat window. Let me know if any one or two are able to log in. Okay. You can use your social media ID also. If you have IBM ID, you can use that. No need to do any registration. You can use any of your ID and log in. You will see some welcome page like this. Has anyone logged in? I just want to ensure. Okay, log into this. Okay, you can, since it is getting recorded, I will proceed so that you can watch this later on. And I don't know whether this is demonstrated to you earlier, but I will quickly show this. This is for you to understand, if there are two, say I'll remove this. If there is one qubit computer, we call this as a Q0, okay? And, it is in state like this. I will make this, okay, it is in ground state, okay, right? I will, this is a circuit we talked about, right? I am taking an Hadamet kit, which will put the qubit, right? We have to work with the qubit which is given to us, okay? And which will put this in a superposition state, right? So this is what happens, okay? If I add one more qubit, right? So this leftmost side 0 and 0 is the state of this Q1. Rightmost side 0 and 1 is the state of the qubit Q0. Why? Because that is in the Hadamard superposition state. If I take this also, right, then both will be in the superposition state. Okay, 0 and 1 at the same time. So this is the basically circuit, they will create so that the feature, the optimization, whatever we discussed, right, will happen using the circuit. So this is a C0 gate, which will put the qubit in the entanglement, right? If the state is in 0, that another will be in state 1, like that. Okay, this is entanglement state. Okay. Now the interest here for us is we will quickly go to the lab part. So this program we will quickly see what it does. You'll appreciate what we have discussed so far. Okay, let that comes up. Right. It's a very simple program. Okay. If you want to get into the hackathon, right, to play around with the data, this is a very basic level thing. Okay. And pure Python knowledge is good enough, and then some of the things what we discuss is good enough, right? And see here we are. Qiskit is the open source library. I'm sure you might be familiar with this. IBM is contributing to this, and there are various modules or libraries are coming out for quantum machine learning. Okay, so you have to input, say, feature map. You know that what for feature map? It is for encoding, right? And then you import QSVM, and now you know that we are going to do that, optimization and the SVM part, whatever that coefficients computation, right? That happens in this module, right? And rest are all quantum instances where you use the quantum computer. Okay, so that's a quantum, and then rest are all related to the machine learning, splitting the data and all those stuff, right? Only that much, right, is done. And then here we have taken some simple data. Okay, you can kind of you search for quantum machine learning Qiskit. There will be many other samples available for some other decent data sets. Okay, but here we have a data, simple data. We are splitting. That is the first step we are doing. All right, and then we do the feature map. Okay, and then we do the computation core computation, whatever we discussed, right? And then we kind of execute that in the, here it is basically the simulator I've given. Okay, so once completes, then it is able to come out and say that, okay, then we have validated also. Okay, so 100% is able to predict correctly, okay, for the test data that is given. So those who are familiar with machine learning, you will easily appreciate that, okay, nothing much. Take the data, do your regular flow with the machine learning. And when you're ready with our features, you come and give it to use the feature map to encode and use the algorithms to do your computation. Okay, run it in the quantum, right? And then kind of you go ahead with your prediction. Okay, so that is what the flow, there is nothing much change in our approach. So what is this? QSVM. Yeah, QSVM is there. So the first cell got executed right straight away, and second cell I'm executing. You will see the star there. It's just trying to split the data and all. The second cell also got executed, and this is where you will see that feature mapping happens, and then your this is of course running in the simulator environment, not in the actual quantum. May take a little more time, and then you will see the results coming out. Okay, right, then you will see the results coming out. If you want to run this in the actual quantum environment, I have another program available over here, quantum FDP. Here I have it's a different program together, but the last part will be important for us. Yeah. So you are taking the account from IBM. This is what you have to do, nothing more. Okay, and then you have to say that, okay, which system you are using. Okay, so you have the quantum computer made available from different data centers. Okay, this is from Manila, this is from Melbourne, Australia, this is from Spain. Okay, you have to mention that, and then you have to go ahead and execute your job. Okay, so want to give this to you as a probably homework. If you have any doubt, you can reach out to me for your hackathon requirement, right? So two different programs. One runs on the simulator for the QML, and this one, basically how you will run that same thing in the IBM quantum computer. This is the only cell you have to add. Okay, and you will get the quantum computer details from this page itself. When you go to the composer, when you click here, setup and run, you will see this. Manila is a 5-qubit system, and various other data centers. I don't know where these are all. 1-qubit system also is there. Okay. But anyway, these are all available free of cost, and you know that you have to run the experiment multiple times. Then only you will come to a final result. Okay, so it is little probabilistic here. Okay, the quantum, it is not very deterministic. Okay, why? Because the state of the qubits, maintaining that is a challenge. And I'm sure when you discuss the basic principles of quantum, all this got discussed. Quantum interference and all those things comes into the picture. But you need to be aware that we have to run it multiple times. That is something we reflect in our program also. Okay, here we will mention the shots, which shows that okay, for how long you have to repeat that experiment. Okay. All right. So let me see if I have any questions. So this is a basic introduction of, I think Manjula madam has logged in. Like whether I don't know whether you could able to follow, but since it is recorded, madam, I think you can come here. Composer will help you to do the circuit, and the lab will help you to run the program. Yeah.
Thanks a lot, sir. We'll be sharing the slides and recordings also in the Discord for students to refer later.
Right. Yes, madam. So I think any questions anyone has?
Participants, please free to ask your questions if you're having any.
So hope you got the basic idea of why we are getting into quantum for machine learning.
Yes, sir. Yes, sir. We understood, and thanks for your time also, sir, for all your exercises.
How to integrate quantum with Keras, Deepak? See, Keras will give you the framework for your machine learning, deep learning related. Okay, it will help you to provide the library for your feature extraction and all the stuff. Okay, now you should be able to answer this. Why? Because the main point what we stressed or discussed today is you do whatever things you want to probably with Keras. Okay, but the point here is when it comes to you are ready to give your data for your computational requirement. Okay, the starting point for the quantum is you encode the data, does the computation, and then try to interpret the data. Okay, these three things are important. Okay, now whether Keras and this Qiskit library can be combined, that experimentation I have not done. Okay, right, but Qiskit itself is good enough to give you the feature for you to do the rest of the manipulation that you want to do with the data. Okay, so this combination, all those things, I think someone has to try and come out with a paper, right? But the basic idea is you are free to do in the classical world all your machine learning other requirement, right? Cleaning, processing, feature reduction. That is why the last diagram, that green and blue, right? PCA, everything you do in the classical world. And when you come to quantum for your computational requirement. Okay, hope that answers. All right.
So, yes, sir. Is there any more questions you would like to ask Rajesh, sir? So, if there are no more questions, then, sir, thank you so much for your valuable time and imparting your knowledge with us. And we'd like to express our sincere gratitude for explaining how to get into ML. So, since I'm a beginner, I found it very useful. Thank you so much, sir. And Participants, if you have any issues regarding this event, please feel free to contact us. I would like to remind again that this is the last session of the workshop today. So we hope you found all our sessions informative and useful for the working of this hackathon. So we hope you all have started with the ideas and working on it. You can submit your ideas till October 20th, 2 p.m. If anyone has issues regarding team formation, feel free to use the general discussion channel in Discord to form and manage teams. So the links all will be provided, of all the sessions will be provided in Discord and Hype. Thank you everyone. Thanks for connecting. Have a great day ahead. Thank you, sir. Thank you, ma'am.
Thank you, madam, for giving me the opportunity. My pleasure interacting with you all. Thank you all. Yeah.